Hi, so the part 3 of this topic is talking about the net positive suction head NPSH required and available. So it's used to assess the prevention of cavitation, as addresses the effects of the vapor pressure of the fluid being pumped on the onset cavitation. So to avoid cavitation, you must meet the net positive suction head required for the selected pump. And that's why you have enough available to make sure will not impact on the performance of the pump. So you need to pay attention to the suction line as the fluid passes through before reaching the pump, because that's where the flow direction from the suction line, then discharge line. The design of the suction line must provide sufficient high pressure to avoid development of vapor bubbles. These bubbles could be through the temperature of the fluid and the pressure, and they could cause cavitation. Cavitation, I'd recommend you to watch this YouTube video, which I'll play it in the class, but you can copy this link and you can find it. It's suction pressure at the pump inlet is too low. Vapor bubbles from in the fluid in a manner similar to the boiling. The fluid enters the pump through the suction port at the impeller central eye, and where the lowest pressure occurs. Rotation of the impeller then accelerates the fluid outwards along the vents towards the casing called a willet. Fluid pressure continues to rise throughout this process. If the vapor bubbles had formed in the suction port because of the excessively low pressure there, they will collapse as they followed into the higher pressure zones. Collapsing bubbles releases large amount of energy, effectively extracting impact forces on the impeller vents and causing rapid surface erosion. The textbooks provided chapter 13, table 13.2, vapor pressure and vapor pressure head of water at different temperatures in degrees Celsius from 0 to 100. And you can see the vapor pressure kilopascal, specific weight for the water, and as well the vapor pressure head calculated here in this equation. So the equations we use from these textbooks, you have HVP equals the VP vapor divided by gamma, specific weight. We call it the vapor pressure head of the fluid in meters. And then you have the vapor pressure, absolute value of the fluid at the pumping temperature. Then you, based on that, you calculate the net positive suction head must be, based on the assumption of these textbooks, they assume it is 1.1 higher than the required. To calculate the available, you have the HSP represent for us the static pressure absolute above the fluid in the tank. You can see it, that's the HS. And then you will get the HSP of the tank, the pressure head. HS is from center line for inlet to the pump to the surface edge, and that could be plus or minus. So if the pump is above the reservoir, it will be negative. If it's on the pump under the reservoir, will be positive. Minus HL represent for us head loss in suction pipe due to friction and minor losses. That's the one we calculated in the part 1. And you have the H vapor, which is the one you get based on the temperature from this table, 13.2. So this is the question: determine the available net positive suction head for the system shown below. The fluid reservoir is a closed tank with a pressure of minus 20 kilopascal above the water. At 70 degrees Celsius, the atmospheric pressure is 100.5 kilopascal. The water level in the tank is 2.5 meters above the pump inlet. That's telling you HS would be positive. The pipe is DN 40 schedule 40 steel pipe with a total length of 12 meters. The elbow is a standard, that one, and the valve is a fully open globe valve, and the flow rate is 95 liters per minute. Then calculate the maximum allowable NPSH required for the pump in the system. So we highlight the information as you see them here, the numbers given to us in the question. We write the general equation, net positive section head available equals HSP plus minus HS minus HL minus H vapor. To calculate the absolute value, you have the atmospheric plus the gauge. The gauge is in vacuum, so it would be minus 20 kilopascal with the atmospheric pressure 100.5 kilopascal. The HSP here will be the absolute value we just calculated divided by gamma, the specific weight. We choose it at water 70 degrees, which will give you the specific weight from table A1, appendix 1, and 9.59 times 10 to the power 3. That's because we're moving from kilopascal and kilopascal to cancel each one. And we'll give you 8.39 meters. HS, because as stated, is above the pump, it's positive 2.5. It's given with the following value here. That's the HS. Now, to find the friction losses, HF, for the pipe in schedule 40, the denominal 40 schedule 40, you go and find that DN is 40. He is giving you the DN, not the 1.5 inch. And based on that, you can determine, it's giving to us the Q to determine the velocity. So velocity equals Q divided by area. The area, you find it from here, is 1.314 times 10 to the power minus 3, and 95 divided by 60,000 to convert from liters per minute to meters cubic per second. You get the velocity 1.21 meters per second. Then Reynolds number, VD over kinematic viscosity. V is 1.21, just calculate it, and D is the 40.9 divided by 1,000 and divided by kinematic viscosity. You get it from table A1, which is this value, or one of the values. You go to kinematic viscosity. Then you get that 1.2 times 10 to the power 5 turbulent flow. That's actually table A1, which is giving you the 4.11 times 10 to the power minus 7 kinematic viscosity. Two options: either you go to Moody chart and you find that from Moody chart calculator or Moody chart itself, and you have the E over D. So we're using steel commercial pipe. The roughness is 4.6 times 10 to the power minus 5. And then the diameter, you get that ratio 0.0112. You put the Reynolds number and Moody calculators with the relative roughness. You get the friction factor is about 0.022, or you can use the equations similar to what I've done in part 1. It's up to you. Like, you should go through it. You write Darcy equation, HL losses F L over dV squared over 2G, 0.022 times 12 divided by, so that is L over D. You convert the diameter to meters, V squared over 2G, you get 0.48. That is the losses in the system. So all of this, we're trying to find these equations to help us. The last one is left for us is H vapor, because it's the water at 70 degrees. So we could use straightforward this value, vapor pressure, or the pressure head straightforward 3.25. Okay. So that what I say, and then you put the values, and then you get exactly the net positive section. You get the net positive section head available 6.506 by substituting the values, and then the required is the available divided by 1.1, so 5.91 meters. That's what the system going through it. Now, to select the pump for this question, we go to 1.5 inch times 3 with 6 inch is the impeller diameter, 1,700. You can choose the 95 liters per minute. You go to the selection of that, let's say 5 inch, and then you read the net positive section head required. It's for this pump. If I selected this pump, it's less than 0.5 meters. So the available, it's actually higher than what is required, which is good for that type of pump. Go through it. So let's try to solve it with respect to our question. All right, so to go for the problem we're trying to solve, so I just took a picture for this section, and then we see how can we get that is done with respect to the problem we're trying to solve. So basically, you have the following: the H equation available, HSP plus minus HS and minus HL and H vapor. We know from the problem itself that the question giving to us, the temperature is 15 degrees. And we know as well that the pump is below the tank, so the surface of the tank. So all this information will help us. So first thing, we want to start with calculating HSP. So to do that, HSP equals for us will be the absolute value. So it would be 105 value plus the gauge is 0 because you can see it's vented. All of that divided by, I put the brackets, divided by gamma. So gamma for what is we trying to use is the specific weight. So I go there and I select my specific weight, 9.81. You go through it and then you come here, click enter, you find the value, it's 10.244, I put meters. Now I'll put the equation next to it. I'll show that in a very few seconds in a video. I'll show you the equations going through it. So that is HSP. HL, it's the losses. By the way, I always prefer use the following subscript, and this one as well, subscript. Organize it nicely. HL is the losses. Losses is calculated for the suction line, which we could got them. So we go to the example we calculated, and technically H losses is this one. So I could come back here and I would say sum equals, and I go to example. These are the energy losses we calculated, and close the brackets, and you get that value. And that way you can find it. If it's something really gone, what I usually do here, trying to put summation that side, and you go there and you can just bring that value, which is the same, identical from example 0.038, 0.38. All right, again, that is a meter. So again, we're talking about the suction line for that. HL, we got these values. All right, what's next we need to do is to calculate the following values required for our example. So what are the required things we need to do is H vapor. So we got HSP, we got H losses, H vapor, H VP. Again, I like to make sure this one go subscript. H vapor, that will be calculated from table 13.2. So I will bring table 13, which the one we did before. It's the one giving you the values for the pressure. So you come here and you can see at the question, the problem is 15 degrees Celsius. So 15, it's in between that. That's where required some type of interpolation because we don't have that value. There is another option if you don't have that table. It's technically you can select that, doing it with respect to selecting different values from it. So either table 13.2 and you do some interpolation, or you go through it. So after interpolation, this value will be close to 0.18, and that would be in meters as well. So interpolation for it. Now, net positive section head available. I need another value, which we haven't done yet. I will put it very soon. HS, it's something I haven't done yet. HS is positive. It's in the question itself given because it's the pump below the surface. So that is 2.4. And again, that is meters. Now in the equation, I will follow this following. This one plus HS minus HL minus H vapor. Following exactly the equation, and then you get the answer in meters, which is 12.426. That's the net positive section head available. Now the textbooks assumes 1.1 net positive section head required. I'll put it that one here. Subscript. It's equals to the value. So to find that is like you just rearrange the equation to make sure the available you go. So you kind of what is required, it should be a small value based on what you can find. So if we go to the chart, the equation we solved before, you find the available in this problem, it's around 3 based on my chart. And so the required, I can say, is 3 meters. That it's from the chart, from the pump chart. Okay. And that represent for me with the 850. So that is at the desired point, or 850 liters per minute. Okay, which is very difficult to see, but it's around 3 or 2.8 is less or low. So I got 3 meters in case of that. So that will give me, if I multiply that with the ratio, so the net positive section head required, just make sure you go with that value. So it would be equals that one times 1.1. So the required will be 3.8 meters, but the available is 12. So you have the available technically is higher than what is required by the system. So the available, it's a lot. So you can say the net positive section head available, it's technically bigger than net positive section head required. And again, we can just make sure these are subscripts. Just organize them nicely. So that it's technically, it's proving your design is it's safe and no problems. I don't have problems in the design, because technically I have 12.42 meters available based on the pump I selected. However, the required by the desired point, which is at 850 liters per minute, is about 3.3 meters based on the chart and you selected. So based on that diagram here, selected that with the retire. So this is a good for the 9. It's actually is lower than that, but I went more like to make sure like my design is all safe. And that is really what we need to show with respect to the chart and how you go through it. So you could definitely can show this here. I would just take a photo and put it in here so you can show it nicely with your design, and that way you can show your desire and what's required. So it's possibly that value is 2.8. If it was, I'm going with that value, and you see how everything is changed. And definitely my net positive section head available is bigger than the required. My design is safe in that way, and you go through it. So that it's technically the last part of this question about the net calculating the net positive section head available and comparing it with the required to make sure my design is safe, following the assignment, the assumptions made by the textbook. And possibly when you work in industry, they have more conservative required, and that depends on the application. Thank you. Hopefully these videos, the 3 parts, will help you with the assignment, final project assignment for this paper.